Good morning. Today we'll be doing a bit more algebraic stuff, namely we'll be looking at the inclusion-exclusion principle and how to apply it for exponential time algorithm, and also something called fast subset convolution, which is something between inclusion-exclusion and a Fourier transform. We'll see how it works. So that's what we'll be doing here, and this will be like much more algebraic and much less pictures than what we are used to. So this will be really like this slide is really like title slide and 10 slides filled with equations. I hope to explain you these equations. I hope you to explain what's going on there and draw some pictures in the margin, but like be prepared for a more algebraic lecture today than the usual graph theory one that was before. Okay, so we start with something that Michał already touched on one of the lectures, namely the dynamic programming over subset lattice. So we have got some universe U, and we are looking at all subsets of this universe. And this subset lattice, you can think of it as like a diamond. Yeah, sometimes somebody draws it as a diamond. So at the beginning, you have at the bottom you have got the empty set, at the top you have got the entire set U, and in the middle there's like a lot of sets. So like size of U, choose size of U half, sets like of size half, etc. And like going up, it's going to a superset, and going down, it's going to a subset. You can draw this subset lattice like this, and this really should look like this diamond should really look like this. Yeah, because I mean, there's a lot of sets in the middle. These sets in the middle, there's a lot of them, and there are very few sets and like of size much different than half of the size of the size of the universe. Okay, so this is our subset lattice, and the structure of being a subset, it's really like something on which sometimes you can make dynamic programming algorithm. And Michał showed you a dynamic programming algorithm for set cover that used to do this, like had state for every subset up here, and somehow builds like for the subset cover problem, when you want to cover the entire universe with at most k sets from your given family, you are building like how which subset of the universe you can cover with how many sets from the family, and you like grow and grow this dynamic programming table and get some sort of this running time. But you need also this space, because you are keeping like a track, like you have a memory cell for every subset of the universe. What's the minimum number of sets, what's the minimum number of sets that can cover this subset? This is your sub problem in dynamic programming algorithm. Okay, so this is something that Michał showed you at some moment. And the second example given by Michał was Steiner tree problem, which was slightly more complicated. This was the graph theory problem, and maybe one of the very few graph theory problems today. There was a graph, and there were some terminals there that you want to connect, and you want to pick another color, say black, and you want to add as few vertices as possible to connect these guys and make everything connected inside. Yeah, so you have got some terminals, these are these blue guys, and you want to add the black guys, at most k new black guys, to make the blue-black graph connected. So this is the Steiner tree, and Michał showed you that if you think of the universe as being terminals, like which terminals you already connected, then you have this dynamic programming state, like which terminals you already connected, and at which extra vertex is like the black root vertex, the connecting vertex. And for this ones, you think of like some array cell of V and S. What's the minimum cost of connecting S and V, so that you can start from V to build more, like to continue building the tree from the vertex V. This is a vertex in the vertex. So this was the dynamic programming that Michał presented there, and it had the space to do times the size of the graph. Here it's this exponential factor in the space complexity was 2 to the number of terminals, because for every subset of the terminals and every vertex extra, you wanted one cell was the minimum cost of connecting these guys. But the time needed was like 3 to the number of terminals, because there were sometimes when the trees merge, when two trees merge, and there are some S1 here terminals and some S2 terminals here, and you get as total number of terminals you connected, you need to like iterate over all partitions of S into S1 and S2 to find the correct way of like combining two smaller solutions to one large solution. And this gave this 3 to the t time, like the number of like subsets S and partitions at S1 and S2, this is like 3 to the t. Okay, so that was the two examples that Michał gave a while ago. And the third example that I want us to focus today, it wasn't presented last time, was the coloring problem. So we want essentially to compute the chromatic number of the graph. So we are given as a decision problem, we're given a graph and an integer, like this integer is given on input. And we want to check if, we want to test if this graph is k-colorable. And you can actually think of this one as really the set cover problem, because if you think about this problem, this is really like covering the vertex set of the graph with independent sets. So you want to cover the, you can think of the coloring problem as like cover the vertices of the graph as minimum number of independent sets of the graph, and like this independent sets is not given as explicit family, but this graph encodes the family of independent sets. Yeah, so this is like a set cover problem when the universe is a set of vertices there, and the set family is the set of all independent sets. It's not given explicitly as a family, um, but it's given like implicitly as a graph. Like you can use any independent set in this graph as a set in a family, and the number of colors is like the minimum size of a solution of a set cover problem here. Yes, because you need to color every vertex of the graph, and one color encodes an independent set. Okay, so this is encoding, and so you can apply this algorithm. And if you look at this algorithm, well, this is to the u, this is to the n, to the number of vertices, and this, I mean, a priori, if we don't know anything, this is to the n, without any thinking. So this gives 4 to the n running time bound. But if you think about this dynamic programming algorithm, it's really like, okay, so how many colors you need to cover this set of vertices? This is really this dynamic programming we are using here. And if you think about this is like the recursion here is like to cover X, you're iterating over all independent sets inside X, and you're looking, okay, I use one color for this independent set and color the rest with the remaining colors. So this is really your recursion you're doing here, and this is really free to do. If you do it naively, this is really free to do, yeah, because you're, for every set, you're looking at all the subsets, and if this is independent, then looking at some cell. So this gives free to the n running time bound naively. But then you can also use something that maybe Wojtek will be discussing with you in details on the tutorials. There is like a simple graph, really simple graph theoretical fact that if you look, you can enumerate all in the maximal independence. So you can think of these ones as really only maximal independent sets. You're okay if you want to partition into independent sets, you may not use the maximal ones, but if you want to cover the graph with independent sets, you can as well use maximal ones. So think of like being able to color a vertex with few colors, and that's even worse for you, because I mean, if he has got few colors, he has got more constraints what the colors of the neighbors can be. So we can use maximal independent sets here. And now yeah, and now there's a quite simple observation that if you want to enumerate all maximal independences in a graph, you will actually spend this amount of time at most. And the worst case is like this joint family of triangles. This is the worst case up there. And you can actually enumerate all maximal independences within this running time bound timestamp polynomial. So timestamp polynomial. And so in this way, you can do this minimization. Like look, in this minimization, you can really do 3 to the size of x over 3. This minimization can be done really in this time. So you think of this like this the running time bound now becomes sum over x within v of g 3 to the over 3. And this is really like you sum over subsets 3 to the size. This is really 1 plus square root of 3 to n. Yeah, so this is really something. So this is like 2.4 or something, for something to the n. Okay, so this is not really 3 to the n. This is really 2.4 something to the n. I don't know by heart the third root of 3. What's the decimal expansion of this one? Okay, that was quite quick. Maybe Wojtek will be doing some discussion this maximal independence of this tutorial. This is not the essence of this lecture, but this what I wanted to say here is that this K coloring problem, this is really a set cover problem. And if you write the recursion and like understand that you're really iterating over maximal independent sets below it, then you get a running time bound of the form 1 plus third root of 3 to the n just by doing this recursion and enumerating independent sets within X, maximal independent sets within X, using using like correct recursion to enumerate them to get the good enumeration algorithm up there. It's not very complicated. I mean, this theorem is not very complicated inside it. It's just observing how to good, how to well enumerate them. Okay, so that's the subset lattice. I mean, recalling subset lattice. And now I want to do it smarter. So now the first thing I want to do, I want to more or less keep the running time bound. I want to more or less keep the running time bound, but I want to worry about space. It's like a bit from like maybe like if you try to implement some of this algorithm, if you try to implement some of the exponential time algorithm, you quite often hit the barrier of space rather than running time bound. For running time bound, okay, maybe you will need stronger computer, or maybe try to somehow like make it more distributed, or like just leave it for a few nights at the computer, maybe it will work out. But once you run out of space and run out of your random access memory, and your program starts to write things on the disk, you're in a hopeless position. Like if you start writing on a disk and caching things on the disk during the running time bound, this is like the end of your computation usually. So let's try to look, can we limit the space here, keeping the running time bound, uh, keeping the running time bound as it was, or maybe slightly worse or similar to what it was. And the key here is this inclusion-exclusion principle that you know probably from discrete math and probably you have seen before. This is a very concise way of writing it. The way you are probably used to is that if you want to look at, like, if you want to look at, okay, what's the, if you want to look at the sum of a lot of things, so maybe let me write it here. If you want to count the number of guys in a union of a few sets, then, well, you can actually look at all the sets, blah, 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 blah. But then, oh, actually you realize that you overcounted. Like if the guy was in two sets or more, you overcounted. So let's subtract. Okay, maybe you overcounted some guys here, maybe you overcounted some guys here. Okay, so you subtract all these guys, and then you subtracted too much. If the guys was in three sets, then you added it 3 times here and subtracted it 3 times here. So maybe you should get back the intersections of the three guys, etc. And the inclusion-exclusion principle says that if you do it to the end, like all to the end choices of like which sets you count and which sets you don't count, then actually you get the correct summation. So what I wrote here is that instead of looking at the union of all these guys, I'm looking at the intersection of the complements. Yeah. So this is S minus the union of the guys. S is the universe here. To distinguish from the universe from the previous slide in set cover, here the universe is called S. And if I'm looking at the like maybe the complement of the union of all the guys, I need to like, okay, take everything, subtract. So this is like take everything, subtract all the guys, add back all the intersection of pairs, subtract intersection of triples, blah, blah, blah. This is what really this one says. And if you want the formal proof here, it's really like counting how many times each element is counted on each side. So pick one guy from the universe and see how much times it's counted here and how much times it's counted here, how many times it's counted here. Well, so let's look. Jx is inside which sets? It's the indices of the sets that contain this element. So in which at AIs this element is contained. And on the left hand side, we are just counting the guys that are in in this intersection of the complements. Yeah, so they're in no of the sets AI. If the JX is empty, so no set AI contains X. These guys we count on the left hand side, and on the right hand side, if you look at this ones, well, where does the X will appear? The X will appear here whenever I is contained in JX. Yeah, whenever this guy is in this intersection. Whenever this guy is in this intersection, the element X will be counted here. So it will be counted like for every I inside JX, it will be counted, but like there will be sign plus or minus depending on the parity of the size of I. Okay, so what we are doing here, we are really counting. We are really counting for all subsets of JX, like -1 to the size of the subsets, and this is like 1 minus 1 to the size of JX. If JX is not empty, but if JX is empty, there's only one guy in the sum, and this is 1. So this is 1 if JX is empty, and 0 otherwise, because this is 0 if JX is not empty. Okay, if JX is not empty. Okay, so this is like really proving the inclusion-exclusion principle, which was probably done also on the discrete maths course in the first year. And yeah, so we'll be doing this ones because sometimes, I mean, the intuition for the inclusion-exclusion principle is that sometimes counting things in the union or like counting things in the intersection of the complement is difficult. It's easier to count the intersections. And this is like the way of extending, of changing one into another. But the thing you pay is this 2 to the m factor here. Yeah, so this is like a summation over 2 to the m size things. And this summation will be now the source of our exponential time complexity. So we'll be doing, we counting something which is complicated. Counting this such things will be easy, but there will be like 2 to the m summation, which which make our algorithm exponential time. Okay, that's hand wavy, but let's go to some examples just to see how it works because it's not very complicated to use. Let's go back to the set cover. Okay, I just copied. This is just copied the formula so that we have got it handy here. Remember set cover. We have got universe U. This is universe for the set cover. Just distinguish just this different universe than the S for the um, for the inclusion-exclusion. We have got some family of sets, and we want to cover the universe with at most k sets. Okay, or we cover the family with the cover the family with minimum number of sets from the family. You can think as an optimization problem here. Okay, so this is set cover, and the idea here is that what we want to look at, we are looking at like, so our universe, the universe for the inclusion exclusion is like tuples of k sets. So we look at the tuples of k sets. This is our like potential solutions. Think like the space of all solutions is a tuple of k sets. Ordered, it's easier to think of them ordered. So think of them ordered, it's slightly easier. So the space of our solution is just a or possible lists of k sets from our family. That's the space of solutions. And AX are these potential solutions that make a mistake on element X. So these are the guys that miss covering X. Okay, these are the guys that miss X and they don't cover X. Okay, so this, and so like our index, our list of indices, this is really the universe. So we think of M being as the size of the universe from the set cover, so that yeah, so you think of yeah, so you can think of the universe as numbers from 1 to m, and this is our definition of m. Okay, so think of AX, and now the observation is that this is what we are really interested in. Is there any, I mean, this is the number of tuples, the number of potential solutions that cover everything, that don't miss anybody. Okay, these are the guys that don't miss anybody here. Okay, so this is really what we are interested. We're really interested in the question whether this is zero or not, whether this is greater than zero or not, whether there is any solution that misses everybody, that misses nobody. So like everybody's covered. So it's in no AX. Yeah, AX. Remember, this is these solutions that are wrong because they don't cover X. Okay. So okay, this is difficult. So maybe let's look at this side. So what's really intersection of what's really this term? Well, this term, I mean, you can think of this iteration like this is I, but this one is U. Yeah, this one is our universe. We made assumption that the universe numbers from 1 to m. So it's really like this intersection. It's really like, okay, so these are the guys that miss everybody from I. Yeah, because this is the intersection of AX. AX is the guys that miss X. So if you are intersecting, like if you are looking at intersecting, you're just missing like X and Y and Z and whatever is in this set I. Okay. So, and this is really easy to count. Yeah. You are just looking at these guys from the family that cover nobody from I. Yeah. You are looking at all the sets that miss all of them. Yeah. That miss all of them and just count all k tuples of them. So just this to the power k. Okay, so this is like how many sets I have made my family that completely miss the entire I, completely miss the entire I, and like I just do all the possible k tuples out of them. Okay, so what I would just said here is that, hey, how do I compute here? Like computing these ones is really like size of f times some polynomial, because I need to make computation. These are like non-trivial numbers. I mean, we will discuss numbers at the end, but these are like numbers that may be exponential size. So computation on them is polynomial in the like bit size. Yeah, so there is some non-trivial polynomial coming from the handling numbers here, but really the term here is that the size of the family, because we just need to scan this family and look which guys are disjoint with I and count them and then take k power of these ones and sum with the correct sign all these numbers, and we'll get 0 or more than 0, and this is the answer. If you get 0, there's no solution. If you get more than 0, there's some solution. There's some solution, and we even have got the count on the number of solutions as the form of like tuple ordered tuples of k sets. Okay, so this is something. And what we gained here, well, the running time is 2 to the m, so 2 to the size of the universe, time f times some polynomial. We don't care about the polynomial. We don't compare the polynomial from here and from the dynamic programming algorithm. But the gain here is that we don't have any DP table. We don't have anything to remember. There is just a scanning and computations. The space is polynomial. So the gain here is that the space is polynomial. Yeah, we're just doing iteration over subsets and just scanning how many sets are disjoint with this subset from my family. And this is it. This is all we are doing. And doing some arithmetic computations, which are on big numbers, but not that big, and we can handle it. Okay. So we took the previous algorithm and kept the same exponential time complexity. We didn't analyze the polynomial. I mean, I'm not saying that here the polynomial is the same. Maybe it's even slightly worse, but we don't look at it. But we decreased the space complexity to the polynomial, and this is the gain we get here. So I hope this example, as the simplest example, is somewhat clear for you. If there are any questions, this is a very good moment to ask. If not, then I'm going to the second example. I'm going now to do exactly the same as I did here, but for the chromatic number problem, for the coloring problem. Okay, so now I'm going to compute the chromatic number of the graph using exactly the same trick. Okay, and just because, so this is like the summary here that I just wrote. Just because the slide is slightly longer, the inclusion-exclusion principle didn't fit. So I hope we are slowly accustomed to it, and we'll be looking and we'll be remembering what's going on there. But now we are doing the same set cover thing. Yeah, so there was like the intersection of the intersection of the complement of AX is like some -1, and there's like the intersection of AX over I in X. Yeah, so this is sum over I. This was the inclusion-exclusion principle. And now what we're doing here, we're doing exactly the same encoding, because as you remember, the K-coloring problem was really a set cover problem where the sets were implicit being independent sets or maximal independent sets in my graph. So let's encode it. So F are independent sets. Again, the space for the inclusion-exclusion is the space of all K tuples of the independent sets. So these are the K tuples of the independent sets. And now my indices for the inclusion-exclusion, this will be the vertices of the graph, because remember previously there were the universe for the set cover. So now the universe for the set cover becomes the vertices of the graph. Okay, and I'm doing like, okay, so these are like K tuples. So think of them, okay, color this independent set with color 1, this independent set with color 2, blah, 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 this independent set with color K, and AV are these colorings or these coloring attempts, let's call them coloring attempts, that never color vertex V, that don't color vertex V. They miss vertex V, they're wrong because of vertex V, okay? And again, I'm looking, is there any coloring that's correct? That means that it's not wrong on any vertex. So we are just checking if the intersection of the complements of AVs is non-empty or not, or is the number of such guys is 0 or not. Okay, so we are really like doing exactly the same. This is what's written here. And now what we have here, well, now let's look at the right-hand side of the inclusion-exclusion. There will be like these terms that are really like intersection, and now let's change it, V inside some I, a V, I just rewrote it with vertex V, and these are like all tuples of independent sets in the graph, all tuples of independent sets in the graph that don't color nobody from I. So these are really independent sets. These are really independent sets in the graph G minus I. So these are like tuples of independent sets that don't contain anybody from I, so that this tuple of K elements will not color anybody from the set I here. Okay. So what we rewrote here, we wrote here that like like the right hand side of the inclusion exclusion formula is really sum over I within vertex of G, sum minus one sign times the number of independent sets of G minus I to the power K. Okay, this is really what we wrote here, that the the right hand side really says, okay, we sum over all subset of the graph, how many independent sets are there, or do subgraph, how many independent sets are there. And this is something, okay, by the Moser and Moore, by the previous thing, Moser-Moore thing, this is really computable in time 3 to the like n minus size of I over 3. Okay, so now you have got the same running time bound because you sum over all subsets. This is 3. Okay, this is n minus sim, but you can like swap the roles of over what we sum, whether you sum over like G minus I or I, doesn't matter. So really the running time bound will be again, this will be the the exponential factor in the running time bound. So this times time polynomial up there, and you have got the same running time in the end, and you have got polynomial time. You're doing polynomial space here. You're doing polynomial space here because what you're really doing here, you are iterating over all subsets of vertices really here, counting the independent sets using just enumeration algorithm that I mentioned that there exists on the previous on the second slide, and just taking the k power of them and summing the numbers with some signs, and to use the inclusion exclusion. So this is all, and we have got this time of algorithm and polynomial space algorithm. But there's one more thing to this. There's one more observation to this picture, namely, okay, we can do better. We can do better because, I mean, we can do better if we go back to using exponential space. So, okay, we got this one, but there's an observation here, okay? But there's an observation here. Let us recall this. Okay, I will just draw this slide and recall what what we are really doing. I will rewrite this thing, sum over x within v of g minus 1 to n minus size of x times the number of independent sets of g of x to the power k. Okay, so I swapped I with the complement of I in the summation. It doesn't matter. Okay, so I sum over the subset of up there. And okay, so what we are doing, we are summing something. This is like 2 to the n sum. This 2 to the n sum. We're summing some numbers, like the number of independent sets inside G of x. And to get polyspace algorithm, for every x, we are from scratch, computing number of independent sets from the enumeration algorithm. Okay, but what I want to say here is that you actually can do it by dynamic programming. Like you can, what's written here is that you can fill the table like f of x being the number of independent sets. Sorry, independent set in G of x. Yeah, independent sets of G of x. This table you can easily fill using dynamic programming. Like for empty set, there's one independent set being empty guy, and otherwise you take the set and you take any vertex, and you count the number of independent sets not containing the first vertex, and you count the number of independent sets containing this vertex. And this is simple recursion. And these are not maximal ones. These are all independent sets. Okay, so you can actually fill this table using first time 2 to the n and 2 to the n space. You can fill this table, and then you can compute the sum using again 2 to the n time reading this table. Okay, so you can either compute this one from scratch all the time and get this time and this space and polynomial space, or you can use your space to get this table of how many independent sets are in this induced subgraph, and then do the summation into the n time. Okay, so using inclusion exclusion here, we not only were able to take the previous algorithm and get it polynomial space without any loss on the exponential factor, but also we're able to like improve, I mean, keep the same exponential space complexity, but improve the running time bound by being slightly smarter and understanding better what we are doing here. Okay, so this is it. And I mean, there are some improvements over this running time bound, but they, with polynomial space, but they didn't yet get to do that. So like it's open, let me write here, big. It's open to get to the n time and polynomial space. This is still open and we don't know how to do it. So there are some improvements over this one. It's like 2.1 something something now, I don't know what, but getting to do the time and polynomial space is still open. Okay, so this was inclusion-exclusion. And I hope this coloring thing, and there may be a few more examples from the tutorials. I haven't seen yet Wojtek's list for this week, so there may be some other examples there. But let's try to now make something more advanced using more or less the same algebraic tricks, but it's a much more useful way of thinking, much more general, much more applicable way of thinking, rather than always taking inclusion exclusion understanding or taking some subset lattice understanding what we are really doing. Sometimes, I mean, this is like some sort of generic operations that we're doing in all these problems, and let's try to understand on some more abstract form what we can do with them. Okay, so the correct formulation, actually the very useful formulation that turned out from applications, was something that's calling a subset product. This is subset some product. It's just called usually convolution or like subset convolution, and this is called the cover product sometimes. What does it mean? So we're looking at so our space is now not subsets or families. This is more general, like a functions that assign to every subset some integer. So we can think of them as like big truth tables. So like 2 to the size of u truth tables that have a number for every subset. So this is like, I mean, this can be like a 0, 1 function, whether something is in my family or not, but this can be also some count or some weights or whatever you want. So these are our ingredients, these functions f and g. Okay, and we now make the operations for them. Maybe the operation, like these are the two convolutions. The convolution, like let's look at the first one. The convolution here is that if I look at the convolution and try to see what's the value of the convolution set x, so this is some set inside u, then I'm looking at all the possible ways of taking x and x inside big universe u. I'm looking at all the possible ways of splitting x into a and b, and like summing f of a times g of b inside this one. Okay, summing of g was. So if you think about like f being one on some family f, so being like one when f is some family within f to the u. So if you think of f as being indicator function of some family of subsets, and the g being some indicator function of some family of subsets, then f product g will be like of x will be the number of partitions x into a plus b, such that a is in f, b is in g, and this is like a disjoint sum. Okay, I mean that's an example. So if f is just indicator function of some family and g also indicator function of family, then the convolution counts how many you can get this set as a union of one set from one family and the disjoint union of this set from the other family. So this is the product. In the cover product, we maybe I will use red color now. In the cover product, you don't have this requirement of being disjoint. Okay, so they now can be like a like that and b like that. They can have a non-empty intersection. So this is really here. This one becomes just a union, not a disjoint union. Okay, not a disjoint union. Okay, so this is like f product g. So if you want the cover product, yeah? If you look at the cover product of two indicator functions, then for x, this is like how many ways you can take one set from one family and the other set from the other family, so that the union is just your set x up there. Okay, so these are our convolutions. They will be useful in a moment. We'll see in a moment how they're useful, but you can see that this is like for even from this example, it like counts how many ways you can take like a few tuples and like yeah. So for example, if you take some f being indicator like that, let me just use now blue color, and you take f product f and k times, okay, and this on set x, this is like in how many ways you can partition x into k sets from this family, into a tuple, ordered tuple of k sets from this family, okay, from this family. So this is how you can use these convolutions. And now we depart from this way of thinking about, I mean, now we depart from the applications of the convolutions, and now we focus on the convolutions and we focus how to count them. Okay, so we are given, so think of the algorithm like we are given f and g as input, so we have got this two tables with 2 to the n numbers or 2 to the size of u numbers. Okay, and we want to compute a table of for the cover product and a table for the normal product, for the subset convolution product. Okay, so we want to compute the table. So the input is of size 2 to the n, and the output is of size 2 to the n. Yeah, so we have got 2 tables of size 2 to the n each on input, and we want to produce 1 table of size 2 to the n on the output. And at the moment, there's one tiny remark with an asterisk that actually one footnote that actually, I mean, I'm now counting arithmetic operations. For the moment, I'm not worrying about size of the numbers I get. These numbers will get bigger and bigger because we are summing producting numbers and there's 2 to the n size. So there will be some non-trivial polynomial factors involved from the arithmetic here. But in the analysis in the next few slides, I will be counting the number of arithmetic operations and be worrying about the size of the numbers at the very end. Okay, so I'm counting additions and multiplications as like one object, and we'll discuss like size of numbers at the very end. Okay, let's go further. Oh, this is the example actually that for set cover, this is actually what I drew here up there. It's written on the slide that actually like for the set cover problem, we're really like taking the indicator function for the set family and taking the k product and checking if everything, if there's a way of to cover everything using k sets. Okay, and for coloring, I taking independent sets and I'm checking the normal product or the cover product. Here it doesn't matter, but sometimes it matters whether we use the cover product or normal product. Yeah, we could use cover product here as well. Okay, we check if the entire vertex set can be partitioned into k independent sets or can be covered with k independent sets. Okay, so this is like the examples I was giving here in the moment. So what we are really doing here, we want to compute this cover product and this product within 2 to the n time. If you look at this definition, so this definition, this is really 3 to the n. If you just do it straight from the definition, the running time bound will be 3 to the n, because I mean, if you want, like, if you have got the full truth table of f and g and want to compute the truth table of f star g, because I mean, for every set x and for every partition, you're making some computation. So these are really 3 to the n operations up there. And if you look here, this is really even 4 to the n operations. Yeah, because I mean, the number of ways, I mean, you don't have disjointness here. So there's like 3 to this sum here is like 3 to the size of x, some number of elements. Okay, because any element can be in A, in B, or in both of them. Okay, so this is complicated, but what we'll see in a moment is that you can actually do 2 to the n times some polynomial, and also to the n space. So I mean, the space is exponential because like the input is exponential, so we no longer care about space. But okay, we don't want to have bigger space than to the n, but we want running time bound to the n. So we don't care about space now, but we care about running time bound. Okay, good. So we continue, and the first idea is that, hey, these products are complicated, but there's a product that's easy to compute. Maybe it's not that useful product, but there's an easy product to compute, namely the pointwise product. Yeah, if you have got two functions f and g, and you want to compute pointwise product defined like this ones, then this is trivial to do it in time to do the n, because you're just taking like pointwise product, and I mean, you cannot do it wrong. I mean, you need to be smart to make it slower than to do the n. Okay, so this is something, and this is the essence of all the Fourier transforms, fast Fourier transforms, and all the like Fourier type operations, that I have got convolution, and I have got also pointwise products, and I want to somehow change the function I'm taking in to change the convolution into a pointwise product, so that I'm doing some transformations on the functions, taking pointwise products and going back by some reverse transformation and prove that what I get by this entire chain of reasoning is really my product, cover product, or my subset convolution product I started from. Okay, so this is what I want to do. And the trick here is that if you look at the computations we're doing in the moment, this will be really very much like inclusion-exclusion principle. So the idea here is like to take this subset lattice, and if I have got some set x here, then sum everything below set x, and to get this as a transform, like summing everything below, this is like the transform. So so this is like, this is called sometimes the zeta transform. This is usually called the zeta transform of function f. So the zeta function of transform m at set x is the sum of the values of all the subsets. Okay, this is sum of the values of all the subsets. And if you think about it, if somebody gave you the truth table of zeta f, you could recover f. Why? Okay, so say there's this diamond, and somebody gave you the value of I don't know how to draw zeta f. If somebody give you the values of zeta f, then well, zeta f of empty set is the same as an empty set because the sum is the same. Okay, so here you know the value here. Let's change the color. Then you know the value here. Then let's take one element. So let's look at f of one element. I don't know, e. Okay, then well, this will be like zeta f of this element minus zeta f of empty set. Yeah, because in the other because zeta of one element, this is this value plus this value. So yeah, so you can recover the single element sets, and you can continue like that. Yeah, so if you know the sums of the values of all the subsets, then you can recover the original values, like going bottom up in this tree and like just computing what you need to subtract and add, and you quickly realize that what you're doing there is really some sort of inclusion exclusion. And okay, that was hand wavy. What really happens here is that you define this inclusion exclusion looking like transform that's doing also like some of the subset what with signs. Yeah, so this is like f of x minus f of like x minus one element, yeah, plus some f of x minus two elements, blah 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 blah. Okay, so this is really like this type of sum. And what you can prove here, and is proven in the next line that will go in there, is that this is really like the inverse operation. Okay, so if somebody gave you zeta f, then you apply this me transformation, which is sometimes called the Möbius transformation. So this is like the fact that this is called the Möbius transformation, Möbius transform here. Okay, so if you look at the zeta, so if somebody gave you zeta, you can apply this type of transformation. This is really this inclusion exclusion that you get the original values. But let's go over this formal proof that you actually have that you actually get the original f. Well, let's apply the definition. So this is the definition of mu. Yeah, this is the definition of the Möbius transform. So I'm taking -1 to the sizes zeta. Then here I'm applying inside the definition of zeta. So this is just sum of subsets. Okay, so first I just applied the definition of mu transform, then I applied the definition of the zeta transform. And now, well, I have got summation, and the only thing you can do when you have two sums is to swap the order of summation. So I'm first summing over all z's. So all the z's that will appear here are subsets of y, which are subsets of x's. So I'm summing really over all subsets of x's, z iterate over all subsets of x's. Okay. And okay, so this f of z, this should be z here. That's my bad, sorry, this should be z here. So this f of z can now go here. It's now independent of the rest of the summation, so I can put it here. And now what's really happening here? Well, I have got really chain here. So I've got x, I'm summing over all y's inside, and I'm summing over all z's inside. Okay? So what I'm really doing, this is a summation here. So what I'm really doing here, I can iterate over all z's inside x, and then iterate over all y primes being y minus z. Okay, and so y. So I can also like think of them. This is x. There is some z inside, and there is some y, and this part is y prime. Okay, so what I'm really doing here is that okay, I'm iterating over like what's bigger than what's the difference between y and z, and there will be like, oh, actually I can think, okay, sorry, here actually the y prime is this one. Sorry, my bad. Actually, y prime is this part. This part is y prime. So y prime is x minus y. Sorry, my bad. Is x minus y. So I can actually look at the remainder, like what's the remainder here, and this is this minus 1 here, x minus y. Okay, so I'm summing over all of them. And if you think about this now, if you look at this picture here, there is z here, and I'm summing over the subsets and taking minus 1 to it. And this will be like 0 if the summation is non-trivial, if this is non-empty, and this will be 0 if x is equals to z. This is this Iverson notation here. Yeah. So the sum over all subsets minus 1 to the size, this is 0 unless you're summing over empty. I mean, unless this x minus 1 is empty. So this is really f of x. Okay, this is really the same algebraic trick that was in the proof of the inclusion-exclusion principle, that summing over minus 1 to the size of subset, this is 0 unless you are taking subset of an empty set, and then it's 1. Okay, so this is the proof. This is really the proof, the inclusion-exclusion. This is really inclusion-exclusion in this proof here, so there's nothing fancy here. And yeah, so we have got this inverse. So we have defined some transforms. Yeah, there's some transforms, but how, are they really useful? I mean, I wouldn't present them if they're not useful. You can think of them as quite, I mean, they're somewhat related to the cover product. I mean, you're covering something and now you're summing over subsets. That seems like something related. So let's check it. Yeah, I mean, what I wanted to say here is that, okay, you can do your homework exercise, and I mean, you can, if you want, you can just try the same operation that if you take zeta of me, then you get also f as before. I mean, this is very analogous. I didn't dare to bother you with like this analogous proof of the reverse operation. So let's go further. And this is like the why we introduced this transforms is that actually, I mean, they move cover product to the pointwise product, like this zeta operation. Okay, so what I'm doing here in this computation, let's go over this computation. I'm looking at the cover product and applied zeta to the cover product. So I'm looking at the cover product and then doing zeta on top of it. Okay, let's do this operation. Well, this is the definition of zeta. I don't know how to draw zeta. Okay, this is the operation of zeta. I mean, there's nothing here. And then we apply the operation of the cover product. Oh, this is the definition of the cover product. Okay, so we are summing over all subsets, and then we are summing over all ways to cover Y with A and B. Okay, this is the definition of the cover product. And now the observation is that really Y is defined here. Like we want to swap the order of summation here. These are really three sums here. Yeah? There's A, B, and Y. But the observation is that once you define A and once you define B, you know what Y is. Yeah? Y is exactly the sum of A and B. So if you choose any A here and inside X and any B inside X, if you choose any A inside and any B inside X, then you know that Y is the sum of U and B, A and B. Okay? So what you're doing here, you're summing over all A's, you're summing over all B's, and now you know that Y is A union B, but you don't really care about this Y. This is just f of A times G of B. Okay? So this summation, if you understand what the summation really does, it sums over all A, all B, and takes f of A and times G of B. And now the observation is that the summation over A is completely independent of the summation over B. Okay, I mean, they're like you sum over A's, you sum over B's. So you can actually write it as a product of sum over A f of A times sum over B G of B. Yeah, because you can look from right to left here. If you now break the parentheses here and multiply everybody with everybody, you will get all the terms here. Yeah, like for any subset A here, for any subset of B here, there will be f of A times G of B here. Okay. And now, okay, but this is zeta f and this is zeta g. Okay, so this is zeta f of x times zeta g of x, this is sum over all the subsets. So what we really did here, what we proved here is that zeta of f time product g is the same as zeta f point y product zeta g. Okay, so we proved this equality, this algebraic equality, that if you take the cover product and then apply zeta, you can as well apply zeta beforehand to f and g and then make pointwise product. And this is very nice because this is this nice product that we know how to compute in time to the end because it's trivial. Okay. And we also know that if you apply me in front of it, these two guys cancel out. These two guys cancel out. So what you get there, let's go, I think it's from the slide, what you get there is that if you want to compute the cover product, you can as well apply zeta to both ingredients of to both coefficients of the cover product, make a pointwise make a pointwise multiplication, and then apply me to get rid of the zeta that's here in front, to get rid of the zeta here. Okay, and this exactly this principle behind all this Fourier transform, all these things. You have got this commutative diagram here that you started with f and g, and you wanted to get to cover product, but instead of going directly, you first take zeta, you take first say zeta, then take pointwise product, and then apply me to go back here. Okay, so this is what we have proven here, that this diagram behaves like that. So instead of doing cover product that has got this 4 to the n time, we are doing pointwise product that has 2 to the n time, but there's one caveat inside it. How do we compute zeta and me? How do we compute zeta and me? If you look at this definition, like zeta f of x is the sum over a inside x f of a, if you look at this definition, then getting from truth table of f to the truth table of zeta f, this requires 3 to the n time. Yeah, because this is like for every subset, we sum over all subsets. Okay, so this is like 3 to the n computation if you do it directly. Okay, so this is to the n, but so far this one is 3 to the n and this one is 3 to the n, because this me is just some -1 signs here, so it doesn't really matter here. Okay, so okay, we have replaced 4 to the n cover product with 3 to the n transforms and 2 to the n product, but this seems unsatisfactory. I mean, we want to get this 3 to the n to 2 to the n, and this requires like a fast zeta transform or fast Möbius transform. Yeah, we don't want to do it naively, we want to do it somewhat quicker. And luckily, this is simple, this is doable, and this is simpler, and this is, I would say, much simpler than like fast Fourier transform or something like that. And this is something called Yates algorithm, and this is known literature since many years. And let me just introduce it. So I have got some function f, and I want to compute zeta f quickly. Okay, I want to compute zeta f quickly. Okay, so let's order the universe. So let's order the universe as like elements from x1 to xn. Okay, and let's think of the prefix of this universe as ui. So ui are the first I elements of the universe. Okay, ui are the first I elements of the universe, and I want to like gradually like change f into zeta f. So I want to change f into something called zeta 1f, into something called zeta 2f, blah blah blah. And what I'm just saying here, okay, so think of the following. Think of this universe as these elements x1 up to xn, okay? There's somewhere index I, and think of my set x, okay, in my set x, there's this element, and this element, and this element, and this element, and this element. This is my set x, okay? So now zeta f summed over all subset of x, f of I. So in this picture is summed over all 32 elements, 2 to the 5, yeah, over all 32 subsets, okay? But now zeta I like looks over only at the subsets of the elements until set I. So I'm allowing, so what I'm summing, okay, I need to take these two guys, but I may not take these guys. I may take the first guy, but not this guy. And I need to take these guys. I may take this guy and this guy. Yeah, and but I need to take these guys. And there will be like 8 such sets here. Okay, so I mean, this was the example on the right. This is the definition. What I'm just saying here is that zeta I, it looks at the set X, okay, and sums, but allows only like taking or not taking elements x1 up to xi, but the rest is fixed. Yes, so we are summing over all subsets of the like first I elements of x. I mean, elements of x that are within the first I elements of the universe, but I'm keeping the rest fixed. Yeah, the rest cannot change. Okay, so this is like my partial zeta transform. And what does it mean partial? The partial means that, okay, this zeta 0 is just f. We are not allowing any changes. I mean, this should say as well. I mean, this sum is like I mean, this is like one element sum, and if I allow changing everybody, then I have got my zeta transform. Okay, so this is like I'm just want to gradually change f into zeta f by allowing this summation. There's this summation of a union inside x f of a. In this summation, I'm allowing to like take or not take more and more elements of x, and I'm just not and like I just move this bar, which guys can be in or out, or which guys need to be in. I mean, to be exact and set x, I progress them from 0 to n. And the main trick here is that, hey, actually, I mean, you can easily change zeta I minus 1 to zeta I. Yeah. So what I'm just saying here is that, okay, let's go to this picture with this universe being like x1 up to xn. And if there's like line I minus 1 and line I, okay, then, okay, I want to compute what the integral. So there's some set, okay, maybe let's do it this way. So there's some set, let's make it like this. Okay, there is some set x, so this is set x, this is set x, okay, and I'm trying to compute zeta I f of x, okay, and what does it mean? Well, this is the sum over all subset of x that are exactly as x on the right hand side of this bar I, but this guys on the left can be in or out. This guys on the left can be in or not in inside my sum. So I'm summing over all subsets here, but I'm keeping this guys fixed. Okay? And the point is that if this element xi is not in x, then this sum is exactly the same. I mean, doesn't matter. I'm just summing over all subsets of x, and I'm not changing anything in this sum. So if this guy is not there, I'm just copying the value from the previous one. But if this guy is inside x, so if xi is inside x, if xi is inside x, then suddenly my summation changes because I mean, the previous summation mandatory took this guy inside my subset, okay? And now I can switch him on and off, okay? So what I'm really doing here is that, okay, if this guy is on, it's just the previous sum, but there's like the number of elements in my sum doubles. There's now all these elements, all the subsets in the summation that don't take this element because I'm now allowed not to take this element up there, okay? But luckily, this is already computed. This is inside my memory cell for the gray set that takes this guys but doesn't take this guy. Okay, if I look at the previous summation for this 5 element set without this 6th element xi, then this is exactly what I want here. I want to take these guys on the right. I don't want to take this guy, but I want to take this. I want to like take or not take all the possible options of taking the guys on the left. So now to compute like the value of zeta of x, this is really taking the previous two values of for x and x minus xi and just summing them up. And this is it. So this computation, this is really like, I mean, this is like looking into two cells. So this is really to do the end computations times n because I need to scan I from 0 to n. I mean, from 1 to n because I start with zeta 0 and I want to end up with zeta n. So I need to n times pass over all x's and make this computation up here. It's in the middle. And this is it. The trick here is that now if the one more thing I want to say here is that I want to take the orange one and I want to say that if I want the Möbius transform, the observation is that, okay, there's this -1 somewhere here. There's some -1s needs to appear here. And what really boils down, it really boils down to replacing this plus with minus, period. If you want to take the Möbius transform. And this all these -1s, because this is really like excluding one element. So this is this one extra -1 that appears in the Möbius transform. So really to make this transform for the Möbius, it's really putting -1 here, minus here, not plus here. And this is it. So essentially the same algorithm, the same trick works for the Möbius transform. I didn't provide you with details here because they're almost the same as I did here. But yeah, the punchline here is that using 2 to the n time and 2 to the n space times some polynomial, you can actually compute Möbius and zeta transform. So as yeah, and observe that you used here additions, only additions here, and for the Möbius one you need to use subtractions Okay, so there are only additions and subtractions here used here. Okay, so as a punchline, if you go back these few slides, and if you go back here to this diagram, this becomes now 2 to the n, this becomes now 2 to the n. So we can compute the cover product by in time to the n times some polynomial, because all these lines are like within time to the n. And we are very happy because now we can do cover product. Now we can go over the slide with this ones, and we have our punchline that we can compute the cover product using 2 to the n times some polynomial, addition, subtractions, and multiplications, because there's this cover product in the this pointwise product in the middle, so there are like 2 to the n multiplications at some moment. Okay, you need to make this pointwise product at some moment. Okay, that's our punchline here. What about this one? So I did the cover product. It was simpler. I mean, the cover product was the simpler one. What about the normal product? The point is that we can hack. Now we are going to use hack. And the hack is to partition the sets according to their cardinalities. That's now the hack we are going to use. And this hack is that, okay, let's define Xi operation, Xi transform. This is not really a very sophisticated transform. This is transform that cuts away all the sets that have got wrong size. So Xx just zeros all the values that have the wrong size of the size of the set different than x. So it just keeps the values of sets of size x. Yeah, you can think of this thing. It just looks at the level k, keeps the values here, and zeros everything else. Okay. And the hack we are going to use here is the following: is that if I want to look at the product, I'm going to look at the cover product, but I'm going to split this cover product into like n square cover products of sets of the correct size. So this is the trick here. I'm taking f, looking at only sets of size k. Now I'm taking f, sorry, this should be g. It should be g here. Okay, I'm looking at only sets of size L here. I'm looking at only sets of size L, making cover product here. So this will be like there will be some sets A and sets B. And now looking only at sets of size K plus L, so that if the guys overlapping guys of size K and L, then the union will be strictly smaller than K plus L. And if the guys are disjoint, A and B, then the union will be of size exactly K plus L. And this behind this arithmetic trick that if you want to compute the normal product disjoint, like disjoint, I mean you want to take set X and partition into sets A and B, what you really want here is that I'm iterating over all possible cardinalities of A and all possible cardinalities of B, making cover product and keeping only the guys that have size K plus L so that they don't overlap between each other. So this is really like a trick that, if I can do the cover product within this running time bound, then, there's the summation of size roughly n square. So I'm by multiplying times u squared, which hides in this polynomial factor, I can do also the normal product, the subset convolution product, by just like sorting the values according to the set size and just doing the cover product there. Okay, so we did this hack and we paid in a polynomial factor a bit, but we can do the second one also with this running time, only the polynomial factor grows here. Okay, that was easy. Once you did the cover product, we did all the hard work using the cover product, and then we observed that the subset convolution product, which is usually more useful or like more restricted, is actually like you can hack it with the cover product. Okay, so this is this one. So we can do also this ones using this. If we don't care about the polynomial, we can also do the same exponential factor in the running time bound up there. Okay, there's one. So there's one caveat here. I said additions, subtractions, multiplications. There are two things. If you are doing integers and you're started with like f and g being like indicator functions of some set or something like that, which is very often the case, then you can observe that all these numbers, they're like exponential in n, there may be like 2 to the n numbers or something like that. What I'm just saying here is that all the numbers, like all the cells, they're like poly of n bit numbers. Okay, so all the numbers inside are polynomial in like the number of bits of the numbers are like polynomial, often also of even linear of the size of the input. So all the operations on them are polynomial in n. So all the operations hide in this poly size of u factor up here because they're like the bit size is polynomial in the size of u, so the operations are like that. The other thing that sometimes useful here is that actually I used only additions, subtractions, multiplications, so that you can plug in your favorite commutative ring here, and it sometimes makes sense to use a field of characteristic 2 inside it or something else. What I just said here is that I mean I only use the fact that the thing is commutative and that I can do addition, subtraction, and multiplications, so you can plug in your favorite commutative ring as the codomain here and it will all work. So it sometimes makes sense to use something stranger than just integers. Okay, just to wrap up then, we define these convolutions and set cover and can be phrased as like question whether like k times convolution, k times cover product or take coloring k times normal product can be larger than 0. So what it really says, there's like a yeah, we proved that these guys can be computed within time 2 to the n times some polynomial and 2 to the n space, just to store all these like truth tables and not much more than the truth tables. And what we get here is that really the set cover and coloring algorithms with 2 to the n running time bound, they really have got now one line proof. Use the fast subset convolution and here you are. This actually, I mean, maybe for set cover and coloring, this is a bit of an overkill, but during tutorials, you will see a number of examples. In particular, there are appearing graphs of bounded tree width, and I think Wojtek will be doing some examples there. In particular, dominating set is the prime example, when actually different types of convolutions like that are very useful to speed up of computations in a join node in a dynamic programming on graphs of bounded tree width. So maybe if you looked at the dominating set problem, how does the joining node for the dominating set problem looks like? It was actually quite complicated. And what Wojtek will observe on the tutorials, or was the hint for the tutorial, is that actually you can use the convolutions to speed up join nodes, for example, in dominating set, but in many other problems. Okay, that's it for I prepared for now. There's 20 minutes left for me how to finish the previous lecture. Are there any questions for that one now?